It is known that the acceleration due to gravity of an object at a distance x from the center of the Earth is proportional to the inverse square of the distance x towards the center of the Earth. Show that if a particle is projected vertically upwards from the Earth's surface with initial speed u meters per second, then its velocity at a distance x from the center is given by that expression there, where g is the gravitational acceleration on the Earth's surface and r is the Earth's radius. So I'll just mention that this isn't the whole question, but it's just one part of the question. But for the moment, I've only written this down because the rest of the question is quite long. Okay, so let's just focus on this part first. Okay, so it's quite involved, but quite doable as well. So let's read this part carefully again. Show that if a particle is projected vertically upwards from the Earth's surface. So here is a key point. We're projecting from the surface of the Earth with initial speed u meters per second, then its velocity is this. Okay, so let's get a diagram drawn, because it's always important to have a diagram so that you can put down all your data. Okay, so here is our makeshift Earth, and the Earth has a radius of r, so this distance is r, and this is the direction that the particle is traveling. It's being launched up or projected vertically upwards from the Earth's surface. So it's actually being launched from here, this point, this tangential point here. So at this point, we can say that t is 0. Our x value, however, is not 0 because x is the distance measured from the center of the Earth, as we're told here, at a distance x from the center of the Earth. So x isn't 0, but in fact it's r, because the Earth's radius is r, and the surface is obviously at a radius or a distance of r away from the center. So x is r, our velocity is capital U, and yes, that's what we have at the moment. But we also have the acceleration given to us. We're told that g is the gravitational acceleration on the Earth's surface. So we've defined this as the positive direction of motion, going up as the positive direction of motion. And so my acceleration, which will be down, is negative g. Cool. So I have this. I have my particles somewhere here, traveling as it's being launched or projected up. And I'm told also that the acceleration due to gravity of an object at a distance x from the center of the Earth is proportional to the inverse square. So that means that the acceleration at any time, or at any distance x, is going to be equal to k over x squared. Great. So what can I write? I can write that my acceleration is going to be minus k on x squared. We have a minus because our direction of motion is up and our acceleration is down. Okay, so dv on dt equals minus k on x squared. I like to have dv on dt instead of a. So we're told that our acceleration is negative g when x is r. This is our initial condition. So when x is r, our acceleration, or dv on dt, is equal to negative g. And so that means that minus g equals minus k over capital R squared. Positive, positive. So k equals g r squared. Great, so my acceleration, which is dv on dt, is equal to negative k, but we've just worked out that k is gr squared over x squared. Great. Okay, so let's have a look at the question again. We have v squared in terms of x. So we need something that relates v to x, and so our dv on dt needs to be altered a little bit, and we use the chain rule. We say dv on dx times dx on dt, which hopefully you can recognize as v times dv dx, because dx on dt is the velocity. So that's equal to minus gr squared over x squared. Okay, and here I want to integrate both sides with respect to x. Integrating v dv dx times dx is the integral of negative g on r squared x squared dx. Great, so here I have the integral of v dv, because these dx cancel each other out. And here I have, well, minus g on r squared is a constant, and I'm integrating x to the negative 2 dx. Alright, and there goes a motorbike in the background. The integral of v is v squared on 2. And the integral of x to the power negative 2, well, we add 1 to the power and we divide by the new power. And of course, I can never forget my constant. Okay, continuing on, we have v squared on 2. Just getting rid of these negatives and bringing this x back down as a positive exponential, a positive power indice, plus c. Alright, now I need to work out my c. Again, I go back to my initial conditions, and the condition was that when x equals r, the velocity was equal to capital U. So that means u squared on 2 equals g r squared on x, but not x, it should be capital R plus c. Okay, I can cancel one of these r's with one of these r's, and rearranging gives me c equals u squared on 2 minus gr. And so therefore, v squared on 2 equals gr squared over x plus u squared on 2 minus gr. Okay, now we just have to put it back into the form that the question wants. So let me bring this u squared on 2 out the front. Plus g r squared. Now if I factor out a gr squared from both of these terms, from the first term I'm left with 1 on x. From the second term I'm left with a 1 over r. Now the question itself had a minus out the front here, had the 1 on r and 1 on x flipped around the other way. So just to suit the question's needs, we can flip it like this. That was v squared on 2, and for v squared by itself we multiply through by 2 and we get u squared minus 2g r squared 1 on r minus 1 on x. And we've proven what we needed to prove. So, part B, calculate the maximum height of the particle above the Earth's surface. Okay, so we're going to be using what we had established in the previous part to find the maximum height. Okay, so what do we know about maximum heights? At the maximum height, at the max height, we have our velocity is going to be equal to 0. So 0 equals u squared minus 2g r squared, 1 on r minus 1 on x. Rearranging a little, I will get 1 on r minus 1 on x equals u squared over 2g r squared. So I've just moved this over here and divided by 2g r squared, all in one step. Now bringing the 1 on x over here and this expression over here, I get 1 on r minus u squared over 2g r squared equals 1 on x. Okay, so I can make a common denominator here, and I'll get 2g r minus u squared over 2g r squared equals 1 on x. Reciprocating both sides, and I'll get x equals 2g r squared over 2gr minus u squared. Okay, so what have I actually worked out here? I've worked out the distance, or an expression, for the maximum height of the particle, not from the Earth's surface, but in fact from the center of the Earth, because that's what x was. In the original question, let's just get it and see. In the original question, we were told that, where are we? That x is the distance from the center of the Earth. But that's not what we want. Our question here has now asked for the maximum height of the particle above the Earth's surface. So I'm going to say let h equal x minus r. Yep, x minus r, because this takes off the radius, and so now it's from the surface of the Earth. So therefore h, which is now the distance from the surface to the point, or to the particle, wherever it is 2gr squared over 2gr minus u squared minus r, which is 2gr squared, let's see if I can fit this on this page, r into 2gr minus u squared over 2gr minus u squared. And yeah, let's just move up here. And h is going to be equal to, if I simplify the top here, this term will be cancelled with this term times r, and I'll be left with negative r times negative u squared, which is ru squared over 2gr minus u squared. And this is the expression for the maximum height of the particle above the Earth's surface. So the surface again was the key point in that question that a student may miss. It's quite easy to just assume that we're looking for x, but in fact we're not looking for x, we're looking for x minus r, which we've defined as h. And so this is our maximum height above the Earth's surface. Part C. If the initial velocity u equals square root of gr, calculate the time it takes to reach the maximum height. Okay, so we have u equal to the square root of gr. Great, so that means that u squared is going to be gr, fine. And now I can substitute this u squared back into what I had from the first part of the question. So let's just find where I've placed that sheet. Here it is, and this is what the first part of the question told us, part A. So our v squared, in this case, in the case where u equals the square root of gr, is going to be, well, it was u squared, so we now know that u squared is gr, minus 2gr squared, 1 on r, minus 1 on x. Now I can do a bit of simplification here, and I'll get 2gr minus, multiplying this term by that will be 2gr, and here I'll have positive 2gr squared on x. And so this is negative gr plus 2gr on x, r squared on x. And then if I took a factor of gr out here and made a common denominator all in one, so I'm doing two steps in one, but it shouldn't be too hard to follow, I'll get, let's see, 2r minus x on x. And that's what v squared is equal to. So let's get v now. V would be plus or minus the square root of this expression. But I can neglect the case where v is negative, and I'll explain why in 1 second. So let's just write it. Yep, I've neglected the negative case, and the reason is we're looking for the initial velocity, we're looking for the time it takes to reach the maximum height. Now, as it reaches the maximum height, it always has a positive velocity because it's always traveling upwards, which we have defined as the positive direction of motion. So it's never going down until after it reaches the maximum height, so therefore we always have a positive velocity in that time. So v is greater than 0. So now that we have this v, I can write my v as dx on dt. That's equal to square root of gr times the square root of 2r minus x on x. Now I'm going to reciprocate both sides, which is the common trick that we've seen in the past few examples. Reciprocating everything, and that's so that we can integrate easier. I'm going to bring the dx up here, and I'm going to bring this square root of root gr here. So I get square root of root gr dt equal to, let's see, x on 2r minus x, and I'll take the square root of that, dx. Great. So now I want to integrate both sides, which is good. If I integrate though without limits, I will get a constant, and I can determine the value of that constant by using certain conditions. That's fine. However, if we add integral limits, then it will be easier for us because we won't have to determine a constant. That will just get wiped out as we do our subbing in of our integral limits. So what do we know? Well, we know at x equal to r, so on the surface, the time is 0. Great. And what else do we know? Well, we want to know the time that it takes to get to the maximum height. So we can define capital T as the time taken to reach the max height. And so now we're looking for t. But what is the corresponding x value at that value? Well, for that, we need to go back to part B, where we worked out the maximum height for this part, where it's x equals, that's the maximum height from the center of the Earth. The h was the maximum height from the surface of the Earth. But since we're dealing with x's here, we're going to use this. So let's see. When u is the square root of gr, so u squared is gr, because that's the condition in our question. That u squared was, where is it? U is the square root of gr, so u squared equals gr. So if I sub that in, what do I get? Let's see, just make sure we can see both things. Yep. So x equals 2g r squared over 2gr minus u squared, which is gr. So that's 2g r squared over gr, which is 2r. Okay, so put that away now. And here are our limits. We're integrating t, the t variable, from t equals 0 to t equals capital T, and we're looking for capital T. That's what we're trying to find. We're integrating the square root of gr dt. And for the x variable, well, I'm going from r, which corresponds to t equals 0, to 2r, which corresponds to t equals capital T. I'm integrating x over 2r minus x dx. Okay, the left-hand side, that's very easy to integrate. Left-hand side is going to be the square root of gr capital T. That's fine. But for the right-hand side, well, let's get some more paper. Okay, so for the right-hand side, this is what we're integrating. Now, hopefully, you're confident enough to see that this integral requires a substitution. And hopefully you can see that the substitution required is to let x equal, what are we going to let x equal? 2r cosine theta, or sine squared theta, it doesn't really matter. I would use sine squared theta actually, because when I differentiate, it will just eliminate a negative sign. So x equals 2r sine squared theta. Cool, so now differentiating, dx on d theta equals 2r times 2 sine theta, drop the power by 1, and times the inside derivative by the chain rule is cos theta. Great. And we also need to change our limits here. So when x equals r, r is 2r sine squared theta, So 1/2 equals sine squared theta. So sine is 1 on root 2, which means theta is pi on 4. And when x equals 2r, 2r equals 2r sine squared theta. And so that's going to tell us that theta is pi on 2. So we're ready to integrate or sub in our substitution. So when x was r, theta is pi on 4. When x is 2r, theta is pi on 2. Now x is what? 2r sine squared theta divided by 2r minus 2r sine squared theta. Great. And I take the square root of that. And now dx is going to be, well, this is 4r sine theta cos theta. So 4r sine theta cos theta and times d theta. So there we've made our substitution. And you'll see now that we have some really nice cancellations happening. So pi on 2, pi on 4. Okay, so in the denominator, if I factored out 2r, I would be left with 2r into 1 minus sine squared theta. And then I can cancel the 2r with this 2r up here. So I'll have sine squared theta on 1 minus sine squared theta. But what's 1 minus sine squared theta? Well, we know that by our basic trig identities, our formulas, that's going to be cos squared theta. So we have sine squared theta over cos squared theta, and I take the square root of that. 4r sine theta cos theta d theta. Alright, continuing on, we'll get more cancellations. Sine squared on cos squared, and I'm taking the square root, will give me sine on cos. So here I have sine on cos. I can cancel the cos in the denominator with the cos here, and I'll be left with sine times 4r times sine. So that's 4r sine squared theta d theta. So this is really all just algebra here, and trig identities and cancellations. Alright, so integrating sine squared. So hopefully you know how to do this, because you should learn it in the 3-unit course, in the extension 1 course. So that's equal to, sine squared theta is equal to 1/2 1 minus cos 2 theta. And now these are things that are relatively simple for us to integrate. If I integrate 1, it's theta. If I integrate cos 2 theta, it's sine 2 theta. And the chain rule tells us I divide by 2. And now my limits are pi on 2 and pi on 4 here. And so now I can go ahead and sub these in. That's 2r pi on 2. Now sine 2 times pi on 2 is sine pi. Sine pi is 0 because of this. This is pi and it's equal to 0. So here is 0. Okay, and minus pi on 4. Subbing pi on 4 into here, I get sine 2 pi on 4 divided by 2, which is sine pi on 2. Sine pi on 2 is here, and it's equal to it's equal to 1 divided by 2 gives it a half here. So here I have a half. So I have 2r pi on 2 minus pi on 4. Let's move it up. Pi on 2 minus pi on 4 is pi on 4. Minus negative a half means plus a half. And if I just distribute that 2 through, I'll get r. Let's see, this should be a capital R, because that's what we made as our substitution, so I'm sorry about that. This should be a capital R all the way through to be consistent. Pi on 2 plus 1, just distributing that 2 through. So that was what the right hand side was equal to. And we said that the left hand side was equal to the square root of gr times t. So therefore, root gr t equals r pi on 2 plus 1. move that away now. Moving that up. And so I can divide by the square root of gr, and I will get, I will have a cancellation here, and it will be r, so root r on root g, pi on 2 plus 1 seconds. And that's how long it takes for our particle to reach the maximum height when the initial velocity is u equal to the square root of gr. The final part says, deduce the escape velocity taking r equal to 6,400 kilometers and g equal to 9.8 meters per second, and that should be squared, meters per second squared. Okay, so the escape velocity. What is the escape velocity? Well, if you've studied physics, or if you're currently studying physics in high school, in year 12, you'll come across the concept of escape velocity in probably the first topic that you do, in the space topic. But escape velocity is the minimum velocity required, the minimum initial velocity required for an object or a particle or whatever to be given such that it escapes the gravitational field of the Earth, in this case the Earth, but in general any planet. So let's just write that down again. Escape velocity is the minimum initial velocity, and by initial I mean the velocity in which it's being launched with. So it's the minimum initial velocity with which the particle, in our case it's the particle, is launched with so that it escapes the Earth's gravitational field. Gravitational field. So when does something escape the Earth's gravitational field? Well, in fact, it can kind of never really escape it. But when we're at an infinite distance away from the Earth, we're said to have escaped the Earth's gravitational field. Although at large distances, the effect of Earth's gravitational pull on us is going to be really insignificant, but technically it's still there. So we have escape velocity. Oh, that's spelled wrong. Escape velocity when x, which is our distance from the center, approaches infinity. Alright, so if x is approaching infinity, let's have a look at our expression for x, which we worked out in part B. Here it is again, x equals 2gr squared divided by 2gr minus u squared. So if x is going to infinity, then the denominator should be going to 0, so that this gets larger and larger. So we had x equals 2gr squared over 2gr minus u squared, capital U squared. Great. And so we want x to go to infinity. So that means that 2gr minus u squared should be 0. The smaller we make the denominator, the larger and larger the fraction gets. That makes sense. So u squared equals 2gr, and so u equals the square root of 2gr. And then if I was to sub these in, I would have 2 times 9.8. Now this is meters per second squared, and here I'm given the, couldn't see that, 9.8 meters per second squared. The radius is 6,400 kilometers. So I need to change kilometers to meters, and by doing that, it's 6,400 times 1,000. And if you calculate that, what do you get? I don't have my calculator here. Anyway, you'll get something close to 11,200 meters per second, or we can write that as kilometers per second, so 11.2 kilometers per second. Okay, and this is our escape velocity. The initial velocity that we need to give the particle so that it escapes the Earth's gravitational field, that's the escape velocity, and we work that out to be 11.2 kilometers per second. And if you went and Googled it, you'll find that this is a pretty rough but close estimation to the real escape velocity of the Earth. You have to factor in things like what the value of g is, because it's not constant around the Earth, and a more accurate value of the radius of the Earth, which also is not constant around the Earth because the Earth isn't a perfect sphere. But anyway, this is a relatively good approximation of the escape velocity.